First, we're going to set the robot's initial position. As you can see, initial pose set. Now, we're going to get it to go to point C, which is here. So I'm going to click this button. Now, we're going to get it to go to point B.
So now we're gonna click return to entrance A, so it'll go back to the starting point.
Now, as you can see here, it's reached point A. And you can see down here, now says waypoint reached, entrance A.
And now we are testing the ladder flooring.
Okay, now we're going to test navigation using camera. Red ball is supposed to stop, green ball is supposed to go. Right now it's stopping.
Green.
Switch to red, it should stop.
Yep, okay. And say that it's going left as well.
Stop it first, stop it first.
Use red to stop first. And then use green to go right. And then show left as well.
So now we're gonna test the QR code. Once it detects the QR code, whatever, let's say it's waypoint 2, then it go to point B. If it's waypoint 3, it'll go to point C. So you can see the QR. As it see point detected, so it will go to the point.
Hello, my name is Abdurrahman, and I explain simulation and the GUI developed for controlling the Turtlebot warehouse navigation system. As you can see here, the simulation environment was created in Gazebo as a warehouse layout. It includes boundary walls, 2 entrance and exit points, 6 racks, stations, and obstacle locations. The racks are arranged in 3 rows by 2 column structure to represent a compact warehouse storage area and fulfill the requirement. This layout was designed to test whether the robot can move through aisles, reach selected rack locations, avoid obstacles, static and dynamic obstacles, and complete the navigation tasks without manual control during the mission. Before the navigation process, the warehouse was mapped using cartographic SLAM. The output map was later defined and finalized to ensure a better experience in the navigation stage. And here's the output map used, as you can see on the screen. Next is the GUI. The GUI controls the navigation stage. The GUI is divided into three main sections. On the left section, there is a rack selection panel. This panel selects the six racks location from R1 to R6. The user can select any racks, select all racks, clear selection, and arrange the order of the selected racks in mission execution. This means the operation can decide exactly which racks the robot should visit and in what sequence. The center part of the GUI displays the warehouse map for better visualization, and the right side of the GUI contains the main navigation controls. The first section allows the user to choose the final exit point, either entrance A or entrance B. Below that, the navigation parameters are displayed, including inflation radius, and much more. The action buttons are also located on the right side. The run mission button starts selected navigation task. When this button is pressed, the GUI generates a run script that sends the selected goals to nav2 using the navigate to host action server. The stop button safely stops the current mission if needed. The return to start button sends the robot back to the starting point. The 2D pause function allows the user to publish the robot's initial pause on the map, which is useful for resetting AMCL localization without the need of resetting the run. And right now, I will leave you with a run where the robot will go through to all racks and then return to the initial position. An obstacle will be added uh, mid-run, and also another 2D pause will be done, and as task will be done to check the 2D pause that's made automatically. And this will be all for my part, and thank you.
Hello, my name is Dave Anand, and this is my individual presentation for ROS. So yeah, so this is my GUI, and this is my gazebo map, and this is my harvest map. So let me just start by doing the 2D post estimate. Okay, now to run the program, I just need to click on any of the racks here that I want to go. So I'll just click this rack and start mission. And now in harvest, it should show the route going there, and in gazebo, it should go there also. And in my GUI here, I also have metrics here. So navigation time, distance, localization error, recoveries, and energy usage. So all of these are going to be used in data analysis later. You can see that in my report. So it's making its way to position track A. It's supposed to go there, wait 5 seconds, then return back to its original position. So okay, yeah, it's reached there, and you could see here reach track A3, waiting 5 seconds, and it should go back. Yeah, it is going back. So for the next run, I'm gonna add obstacles around here. So it's not part of the map. I'm gonna add obstacles around here to see if it's navigating around that one. So let me go home first, then I'll add the obstacles on. Alright, I think it's going home ready. You can see here. Okay, mission complete. Now I'll just add the obstacles here. So let's insert, zoom in. I'll just add obstacles around here. So I'm blocking the whole path, so it doesn't go now. So it's supposed to navigate around this. Just add one more. Now let me just close this. Okay. Let me just align with the ROS map also, so it looks the same. Okay. Close this. Okay. Alright. Sorry, it took a long time. Okay. So now I'm just gonna click on the same rack, and it should. I'm gonna put this as obstacle shift, and I'm gonna click start mission. So it's supposed to navigate around this to go to the rack here. Now in the ROS map, it still shows the same route, but as it gets closer, I think it should change. As you can see here in the ROS map, it shows the obstacles around it, and it's going to navigate around it now. Maybe there's a small hole near the obstacle that's trying to go there. Okay, now it rerouted pretty. So I think there was a small hole here, that's why it tried to go there first. Now it's rerouting to go back to go to the rack A. Okay, once it reaches the rack A3 over there, it should go back home again, and it should not hit this one. It should avoid the obstacle there. And yeah, as you can see, it reroutes back home. Okay, there's also a export CSV function here. So this is just exporting the data from here for me to do data analysis later on. And there's also emergency button here to stop. So yeah, that's about it for the whole ROS individual task. Let me just show you it going home. Alright, I think it reached home. Mission complete. Okay, I think that is it. Thank you. Bye bye.
This is my gazebo warehouse. So this is built using Python XML file and STL codes. So each racks are given its own dimensions, and these dimensions are following a real life warehouse simulation. So based on that, 3 obstacles are added to for the lidar to detect, and the mapping is done based on this. So to open this, the first terminal launches the gazebo world, the second terminal launches the RViz, and the third terminal launches the GUI. So this is my warehouse. Once I'm done mapping using SLAM cartographer, so then after saving the map, we can open the map, and after using 2D pose estimate, it creates an ACML particles around. So there are two ways that we can use the autonomous navigation. Number one, we can, in the RViz, we can select the navigation goal. So let's say if I select this point, so if I select this point, the robot will move to that particular point. So this is not suitable for operators who do not have prior knowledge on using RViz or who do not have the knowledge on terminal coding. So to improve this performance, a GUI is created. So this GUI consists of buttons for each rack. So the gazebo includes 6 racks and 2 entrances. One can be considered entry and exit. And then because the GUI also has the battery percentage shown above here. So if the battery is below 20%, this robot goes back to the charging station, which is entrance 1. Then it has auto route, which means it's like an automatic navigation. So it goes from entrance 1, goes through all the racks and back to entrance 1. So it goes back to the starting. So once I click automated navigation, then if I click on start mission, if you can see, there's a camera preview here so that it helps in safety. Let's say if someone walks in by mistakenly, or if someone is moving the robot, it can be monitored or seen towards the camera over here. So apart from that, it has an emergency stop button for safety purposes. It also has voice commands. If someone is not good with GUIs or anything, they can just shout out the rack numbers, and then based on that, the system will start moving. So there is also navigation log. So this shows the points where the robot has moved. So basically from entrance 1, or the time it takes, the duration, the distance, and also whether it successfully reached that point or not. So the middle part here shows the robot's location. So the robot is currently here, moving to its first location, which is entrance 1. You can see it moving, but you can also see the path it follows. It follows from here to here. So I'm going to test the robustness. If there's an obstacle added at that point, will the robot change its path or not? Since it moved back to the point, it shows that the mission is completed. So now let's test the voice commands.
Good morning, this is Mustafa Karimi, and this is my ROS individual presentation. So let's start off by pasting in the launch file command, and what this does is that it opens Gazebo, RViz, spawns in the turtle bot, turns on nav 2, and also opens my GUI all in one go. Now if we just wait for a second, the GUI should pop up. In the meantime, this is what my warehouse looks like. Okay, so we have the GUI as well now. So first off, let's try setting this position as 2D pose estimate. If I just click this button, then it should automatically set this position as the 2D pose estimate. Now, let's try getting the robot to go to rack A, this one. So as you can see in RViz, it creates a path, this green path in green, and it tries to follow it. And the red line here shows which direction it's currently trying to move in. Now that it has reached the position, let's try and get it to return back to its original position, which was here. Now that I've shown that I can go to racks and come back, now let's test the obstacle avoidance aspect of this. So let's try telling the TurtleBot to go to rack F. Normally, this would be the most optimal path. So let's try blocking it off maybe around here, this aisle section here. So if I put a couple of obstacles and then ask it to go to rack F, let's see what happens. Originally, it will try and follow the original position, the original path that it created. You can see here that it starts to detect that there's obstacles here using the LiDAR. And now it tries to avoid these obstacles. Sometimes if it gets too close to an obstacle or a wall or anything, then what it does is that it backs up by about 1 meter and then tries to create a new route from there. So you can see here that it's following this new route. Okay, one thing I would like to show before ending the presentation here is this feature right here. Export reports. I can use this to save data that has been collected throughout this whole simulation, such as this time here and distance values. Another feature I have is auto localize. So usually you would have to click 2D pose estimate in RViz and then click on the position that the TurtleBot is currently at. But if I use auto localize, it will automatically figure out where the TurtleBot is and set that as 2D pose estimate. And I think that is about it. Thank you for listening.